and that is exactly what I have done, and I plan to show you for 600 particles. So, this is molecular dynamics simulation, 600 particles in a 15 cube box. I have introduced the particles randomly. You can do it in a lattice, does not matter. I have looked at it in time. Time is a misnomer. Actually, what I have plotted is number of iterations, but if you multiply the number of iterations by dt, which delta t, then you essentially get the real time, right. And what I have on the, so this is on the x axis, I have looked at it up to 1000 iterations. You can also look at the energy, and here in the, I look at the black curve is the potential energy, red curve is the kinetic energy, and blue curve is the total energy. What are the particles doing? Here you see the initial potential energy of the system was some value close to 0.6, minus 0.6. So, basically I had started of the system, so that quite a few particles are within the potential well. So, there is some negative potential energy, but as the particles move around, they move to closer to the center of the well, depending upon what kinetic energy they have in initial position. So, you see that the total potential energy is decreasing and fluctuating about some average. This is too short an iteration to claim that it has reached equilibrium, but as the potential energy decreases, what you see is that the kinetic energy increases, thankfully. The kinetic energy starts from plus 1.5, this is all per particle, energy per particle. It starts from 1.5, because that is how we had chosen or rescaled the total velocities when we had introduced the particle, when we had introduced the velocity of particles in the box. It starts from 1.5, but as the potential energy decreases, the kinetic energy decreases to a certain value, but thankfully the total energy remains conserved. You see, it is a perfect straight line, right. How straight is straight? So, let us just zoom in. Now, here you see some slight wiggles coming up, and if you zoom in further, you see that there are significant wiggles. Energy is conserved, but only up to the say fourth place of decimal. And why is that? Because we have chosen dt equal to 0.005, 0.005 whole square. So, your energy calculation is accurate up till 0.005 whole square, right, which is basically the close to the fourth place of decimal, and you see energy fluctuations. Now, if you had done the you had repeated this simulation starting from the same initial condition, but with dt, the integration time constant halved to 0.0025, which I have already done, then what you would get is something like this. So, this blue curve is the total energy of the system for dt equal to 0.0025. What you would see is that the fluctuations in energy are about, even by I estimate, of course, you can quantify it, you can calculate the fluctuations in energy quantitatively, standard deviation of the mean energy once it has reached equilibrium. You can see that the fluctuation in energy by I estimate is about 1/4 here. You have halved dt, the accuracy and energy has gone by dt by 2, previous dt by 2 whole square. So, it is 1/4, right. That is exactly what you see. However, if you look like this, so this is plotted versus number of iterations. I ran the previous code for the same time. So, since I decrease dt, the number of iterations I increase to double, but I did not plot it with respect to time, but I plotted with respect to iterations, and you see within this scale the total energy remains perfectly constant, right, and only when we zoom in can we see the fluctuations. And this is exactly what you should test for your code yourself, and ensure that energy is conserved to the fourth place of decimal, fifth, well, it depends upon the value of dt, as I told you, right. And so, this is a quick test. Now, let me focus on this. You see that the kinetic energy started from 1.5 per particle. You wanted to set the kBt to be 1. So, the kinetic energy per particle by equipartition theorem has to be 3/2 kBt per particle kinetic energy, but it has increased, which means effectively that the average kinetic energy has increased, means that the average temperature of the system has increased. You do want to study the system at an appropriate temperature. So, what do you need? You need a thermostat, you need a way so that you can rescale the velocities to the right by the right amount, so that the average kinetic energy of the system remains at whatever value you want it to be, right. So, I will discuss the algo of the thermostat soon, but what I have done is implemented the thermostat. So, what I am doing is already implemented the thermostat. I shall discuss the algorithm soon after. What I have done is, every time you update the velocity, after a few iterations, once the kinetic energy starts to increase, I reset the velocities, so that the kinetic energy is reset to 1.5 yeah 3/2 kBt, and then again kinetic energy starts to fluctuate. After 100 iterations, in this case after every 100 iterations, I have reset the kinetic energy, so that the average kinetic energy of the system at that iteration is reset to 1.5 kBt. Now, as the MD goes on, the particles are going to move around and kinetic energy is going to change again, is going, potential energy is being changed to kinetic energy is going to be changed to potential energy, and so on so forth. So, kinetic energy will slightly increase, decrease, it can do whatever, but you basically set after every 100 iterations, I am setting it back to 1.5 kBt, and after a few iterations you see that the average kinetic energy is fluctuating about an average even with the reset. Here you can clearly see it, even here you can just about make out. Let me zoom in. You see here there is a distinct jump, here I have reset it, here I have reset it, here I have reset it. So, I am resetting the kinetic energy every 100 steps. What are the consequences? The consequences is that since the velocity of the particles has changed, the amount of displacement has changed, the potential energy initially follows the same graph trajectory as without thermostat, as in this black curve. But since every time you are changing the velocity, the displacements are different, the potential energy also changes differently. So, its basically path has changed. Potential energy here is not being rescaled, only the kinetic energy is being rescaled every 100 iterations. So, for every 100 iterations the energy remains conserved, but when you reset the kinetic energy, the total energy of the system also automatically gets rescaled to this value, and here you call the thermostat again, where you rescale the velocities. So, the kinetic energy gets rescaled, the total energy gets rescaled again. Between this step and this step, you will see that the energy is conserved up till about is conserved to the accuracy of delta t whole square, but in between whenever you call the thermostat, the total energy also gets rescaled, right. And you see here that basically here the energy rescaling is not much. Initially it is much more as the particles move around, as the kinetic energy increases. Here it had basically stabilized to some value which is much higher than kBt, not much higher, but whatever value near 2, and here due to rescaling you see that the total energy also fluctuates about the average. So, basically and between every 2 resetting the energy is conserved. How does one now implement the thermostat? So, that is the topic of our discussion, and let us return to the board. So, coming back to how the thermostat works, we shall be taking the help of the so called equipartition theorem. Okay, just what is a thermostat? A thermostat is a tool, a computational tool, which keeps the temperature of the system constant. So, in the real system, an air conditioner would be a thermostat, because it keeps the temperature of the room fixed at say 25 degrees centigrade. So, here what do we want? We want to study computationally a system which is maintained at a certain temperature, right. So, when I say temperature, it means that energy is no longer conserved. If there is excess kinetic energy due to which basically the temperature increases, because of equipartition theorem, we are using equipartition theorem to calculate the temperature. And then basically as we saw yesterday, that as the particles started moving around in space, there was a decrease in the potential energy in the system, due to which there was an increase in the kinetic energy of the system, and as a consequence the temperature, the instantaneous temperature increases. What do we want? We want to look at a system where the average kinetic energy of the system is maintained at a fixed value at 3/2 n kBt, right, kB being the Boltzmann's constant, which would also mean that the temperature of the system is maintained. Now, you are calculating the kinetic energy at each instant in time. As the particle moves, you are calculating the kinetic energy. Remember, temperature is related to the average kinetic energy. So, a time average of the kinetic energy. But as we saw yesterday, even as the system evolves starting from the initial condition, the kinetic energy itself was increasing. So, even the average would increase. So, the temperature would also increase, and our aim is to keep the temperature fixed. So, the kinetic energy can fluctuate about an average value, but it should not change, because we want to study a canonical system. So, the simplest, so there are many thermostats which are discussed in literature, in the literature of computational physics. I shall discuss the simplest one, and in the simplest one, all that one does is, as the kinetic energy increases, say, one simply rescales the kinetic energy to the right value. Right means at the value that we want, at the value that is determined by kBt, which we want to fix. We want to rescale the kinetic energy to its appropriate value. So, we will essentially take out kinetic. So, we were decreasing the kinetic energy, you can decrease the kinetic energy and fix it to the appropriate value. So, you are taking out energy from the system, right. Now, going to the details. So, suppose the kinetic energy per particle here, you want to maintain it, you have fixed kBt and it should be at 3/2 kBt. We had fixed kBt to be 1 in the simulation. So, we want the average kinetic energy of the system per particle in the denominator per particle to be 1.5. Instead, it was increasing. So, what was the actual kinetic energy? It was some kinetic energy which was increasing as a function of time. So, that is why I have put it as a function of time, and once the system has reached equilibrium, the kinetic energy should fluctuate instantaneously, but the average should be independent of the time. What one could do is define a so called scaling factor. So, you want to basically reduce the kinetic energy. You want to reduce the kinetic energy of the system, so that this relationship is maintained, right? How much should you reduce it by? That is the question we are asking. Okay. So, that is by this. So, for that we have to calculate the scaling factor, which is the kinetic energy actual, that is the one we want, that is the one we want fixed in the simulation. Note the average sign, it can fluctuate though, because potential and kinetic energy will exchange among each other, but the average kinetic energy, suppose this is the one we want to maintain, which is 3/2 kBT. The actual one is when it starts from the initial condition, K E, this subscript stands for system, that is what you are actually seeing, and then you can calculate this prefactor S. So, suppose your actual kinetic energy is we want to be 3/2 kBT, the actual one you see has become 2, right, the actual kinetic energy has become 2, kBT being 1, and then this factor is basically 1.5 by 2, right. You can calculate the square root of S, which you call S1, right. And now, if you scale all the velocities of the system by S1, right, then you would see that. So, if you, so sorry, this is wrong. If you scale all the velocities of the system by S1, right. So, basically S1 is a quantity less than 1, all velocities are being decreased, because you are multiplying every velocity by number lower than 1. Then if you calculate the kinetic energy with this new value of the velocity, you will see that it is basically the kinetic energy of the entire system has been reset to the right value instantaneously, right. So, every particle you are rescaling the velocity of each particle by and getting a new velocity which is lower than the previous velocity, and basically you will see that the kinetic energy of the entire system has become the one which you want. Now, you could do this every 100 iterations, say, I mean how many iterations after you should do will depend upon the value of dt, right. It has to be significantly, the kinetic energy has to significantly change, the microstate has to significantly change, and if you see the kinetic energy has increased, you rescale it back and then let the particles move around with these new values of the velocity, and still if you see that the average kinetic energy has again increased over 100 iterations, rescale it back to the right one. So, the velocity of the system further decreases, more energy has gone out of the system, let the particles move around with in space. So, that again potential, there is exchange of energy between kinetic energy and potential energy, and then again if the kinetic energy increases, you set it back to 1. So, you keep on doing this till you see that the kinetic energy is now fluctuating about an average value, right. So, you take out kinetic energy. On the other hand, you could also have potentials. So, yesterday we saw that there were attractive potentials, the particles were slightly farther apart in the starting, and as the molecular dynamics simulation started, as the position started evolving, the particles were essentially coming closer to each other towards the potential energy minima. So, the potential was decreasing, hence kinetic energy was decreasing. Now, if you have a purely repulsive interaction, right, or you start with an extremely densely packed system, it is also possible that the kinetic energy could decrease. It is not an impossibility, the potential energy is increasing and kinetic energy is decreasing. Then again you use this appropriate expression to rescale. Now, if kinetic energy is decreasing and you want its kinetic energy per particle, you want it to be 1.5 kBT, and you see that it is decreasing, then you again rescale by this factor. Now, kinetic energy, this the term on the numerator will be larger than the kinetic energy of the system. So, you are going to scale the velocities up to maintain the right temperature. Now, when you are calling the thermostat, say after every 100 iterations or say after every 500 iterations, you are basically taking out energy from the system because you are rescaling the kinetic energy. But in between these two steps, energy will be conserved. So, when you apply the thermostat, suppose you update the velocity and calculate the kinetic energy, and every 500 steps check whether the kinetic energy has deviated significantly from the desired value, then you rescale and then you change, you are essentially changing the energy of the system, the total energy of the system as well, right. But in between the calling of two thermostats, the energy will be conserved. So, if you noticed in yesterday's class, there was also the plot of the energy, and that basically was fixed for some time. The kinetic energy and potential energy were changing, and when you call the thermostat, it decreased, there was a jump in the energy, and again it was constant, conserved energy, and when you call the thermostat again, it was, there was a jump, there was a decrease in the total energy because you are taking out kinetic energy. It could also be an increase depending upon the system, and finally it would go something like this, and then it would basically reach equilibrium, right, and then you can start measuring the statistical quantities. Okay. So, you have to wait till the average potential energy, till the potential energy fluctuates about an average, the kinetic energy fluctuates about an average, and then you could say that the system has reached equilibrium, and then you can start measuring statistical quantities, which we shall discuss in the next class, how to calculate statistical quantities, what are the interesting quantities one could calculate. Throughout till now, I have been talking about time and mass equal to 1 and kBT equal to 1. Right. So, without worrying what these things mean. So, let us discuss units. So, that is the basically the topic of the next, our next topic of discussion. So, till now we have been saying that the size of the spheres, the Lennard-Jones particles is 1, kBT is equal to 1. So, everything we set equal to 1, and then we said okay, we are talking about some time, and one does not know what this time means. It is again dt is 0.005 in what units, one does not know. So, let us discuss this topic. So, now I said that we are measuring all lengths in units of sigma, the diameter of the particle. The size of the box is 30 times sigma or 15 times sigma, right. So, that was the unit of length. The unit of energy we had set as kBT. So, all other units, when you say epsilon is 1, it means that its epsilon is 1 times kBT, right, and we had also set mass equal to 1. Now, if you set the values of mass, length and energy, then you automatically get the units of time. Let me explain. So, suppose half mv square. So, half mv square is equal to E, right, I mean the kinetic energy, and it has units of kBT. You can also write it like this, ml square by t square, which is basically I am writing it in dimensions, and it has dimensions of energy, right, ml square by t square has dimensions of energy, and then you can write the dimension of time in terms of ml square by E square root, right. And if we have chosen m equal to 1 and L equal to 1 and kBT, the unit of energy, to be 1, then time comes out to be 1. But again, what does it mean? It means, so when time t equal to 1, it means essentially that a free particle of mass m equal to 1 with kinetic energy kBT, or energy and kinetic energy is of course related to kBT, kBT equal to 1 and velocity of root 3 will take approximately t equal to 1 unit of time to move a distance sigma equal to 1. So, here I have used again half mv square, all that we are using is equipartition theorem, right, because basically if kBT is equal to 1, then V will order be equal to 1, right, half mv square average equal to half kBT, or rather 3 kBT by 2 if it is moving in 3 dimensions. So, basically when t equal to 1, it means that to move a length of the diameter of a particle, sigma equal to 1, diameter of a particle with if kbt equal to 1. So, you fix the average kinetic energy of the system, you fix the average velocity of the system, and a mass of 1 will take 1 time unit to cross the entire diameter. Let us actually put numbers. Now, suppose we were looking your particle which you are modeling in your molecular dynamics simulations is an argon gas particle, right. So, argon gas particle has a mass, atomic mass, atomic weight of 40. One proton is basically 1.7 into 10 to the minus 1.7 into 10 to the minus 27 kg. So, the atomic number of argon is 18, which means it has 18 protons and rest of them is neutrons, right. So, the mass of argon can be calculated to be 1.7 into 40. So, is basically this into 40, which is approximately, we are calculating order of magnitude. So, it is approximately 10 to the minus 26 kg with some prefactors which we are ignoring. You are setting this equal to 1, or you can actually set with all the numbers, you can set that mass equal to 1. So, you are measuring all other masses in units of the argon mass, right. So, you are setting 10 to the minus 26 kg, or if you want to be very precise, this value which is the atomic mass of argon, you are setting that equal to 1, right. Radius of argon is 0.71 angstrom, the diameter is 1.4 angstrom, and this length you are setting it to be 1. Okay. So, you are measuring, when you say that your box size is 30 in some units, in units of the diameter of your particle. So, if your length, if the diameter is 1.4 angstrom, then the simulation box size is 30 into 1.4 angstrom. In yesterday in our computer code, we had uses the box size to be 15. So, the box size is 15 into 1.4 angstroms, right. Energy we have discussed in Ising model as well, can be calculated. The value of kBT in at 300 Kelvin is R by Na, R being the gas constant, Na being the Avogadro's number, and that comes out to be 4.16 into 10 to the minus 21 joules. This unit of energy you are setting to be 1. Okay. Now, if you want to calculate T square, so now we had so if you set everything equal to 1, we had got T equal to 1. So, what does T equal to 1 mean? So, here I am just writing the order of magnitude. So, this is mass 10 to the minus 26, this is L square. So, suppose you take 1 angstrom to be 1 unit of length, or you can exactly put in the numbers 1.4 10 to the minus 10 meter. So, that is what I have put in here, 10 to the minus 10 meter square, L square, and this, and on the denominator you have the value of kBT. And then so if you put in all these values, you see that you get T square to be 2.5 into 10 to the power minus 26 seconds, because now everything has units. So, this is so many seconds, or rather second square, because you are calculating T square, right. And then T, it comes out to be root 2.5 10 to the minus 13 seconds. What does it mean? That an argon gas with at temperature 300 Kelvin on an average has such velocities that to cross a distance of 1.4 angstrom or 1 angstrom, because I have not used the prefactors, I am just talking about order of magnitude, it would take 10 to the minus 13 seconds to cross 1 angstrom at the velocities it will have at T equal to 300 Kelvin, right. Let us take, suppose you were, instead of argon you were modeling some microscopic particle, okay, because L equal to 1. So, we were doing in dimensionless units. Now, suppose you put the dimension of L to be not 1.4 angstrom, but radius is 10 to the power minus 6 meters, 1 micron size. So, you are looking at particles moving around, some suspended gas particles in air, where you are not looking at the atomic scale, you are looking at the molecular dynamics atom of a much larger particle of size 10 to the power minus 6 meters, 1 micron. And suppose the density of that particle was 4000 kg per meter cube, which is essentially 4 times the density of water, because if you write it in kg per meter cube, the density of water is 1000 kg per meter cube, right. Then you can calculate the mass, of the particle, 4 pi r cube. So, 4 pi by 3 r cube into the density. So, you can calculate the mass, assuming we are calculating an order of magnitude. So, pi and 3 cancels, say, and you can get the mass of such a big micron size particle to be 16 into 10 to the power minus 15 kg, right. Here I have missed out the units, but this is kg, because we worked in SI units. The mass of an argon atom was 10 to the power minus 27 kg or 10 to the power minus 26 kg. Here we are looking at a much larger particle. So, the mass is much larger, hardly surprising. The unit of length which we had set equal to 1 is 10 to the power minus 6 meters, microns. KBT remains the same, because we are looking at the same temperature, and you put it back in this formula, T square equal to ml square by E, and you get essentially the value of time, the unit of time which you had set equal to 1 to be root 2 into 2 into 10 to the power minus 3. So, milliseconds, right. There we were getting 10 to the power minus 13 seconds, here it is milliseconds. What does it mean? What does T equal to 1 mean? It means that the time taken by a 1 micron particle which is maintained. So, 1 micron particle, and of course, there are many of them, they are colliding with each other, okay, but a 1 micron particle which is maintained at a temperature of 300 Kelvin, for it to move 1 micron, which is the diameter, or 2 microns, which is the diameter of the particle, it will take milliseconds, or you can put in the numbers and get the exact numbers. But this is the physical picture, this is what it means when I say L equal to 1, M equal to 1, and KBT equal to 1 and time equal to 1. So, this is your unit of time. T equal to 1 means now so many milliseconds, and when you say that your dt is 0.005, it means that dt, it means that essentially that your dt is 0.005 into t, which has been set to 1, right. So, this into milliseconds, square root 2 into 2 into 10 to the minus 3 milliseconds. So, that is what the value of dt is, your integration time constant, right. Okay.